Hello, everyone. Thank you for joining us for this session about enhanced production testing of the Tessent MissionMode. So it's not a different IST approach, but it's enhancement of it in terms of test coverage. Want to use this one? Next. Cool. Okay. So my name is David. I come from Israel. Um, I managed the DFT team in the VLSI group for the imaging radar in Mobileye. I've been in this industry for just over 20 years, done mostly every position in the VLSI. You can find me on LinkedIn if you want to further discuss. So today, as said, I will not tell you about how the good experience we had with the Tessent DFT solution, because it was good. We've used it for all of our DFT for boundary scan, MBIST scan, and LBIST. Everything very successfully, and just recently done a smooth silicon bring up. Thank you, Tessent, for that. But we do want to tell you about how we enhanced the test coverage of the mission mode logic from Tessent, and why, if you intend to use mission mode logic, you should do so yourself. Okay. Before I start with the technical presentation, let me please share a few interesting facts about my company, really quick. So, as said, I come from Mobileye. I work for Mobileye, and Mobileye was founded 25 years ago as a visionary company aiming to save lives. If you check how many people die of car accidents every year, you'll see that the number is over 1 million people. Okay, over 1 million people die of car accidents yearly. And whereas Mobileye was started with like a very simple camera sensor and some computer vision logic or algos, today, more than 200 million vehicles later, Mobileye is a world leader in drive assist. In terms of technology, we can divide our technology into 4 main pillars. So first and foremost is the camera-based sensor and computer vision software. Okay, along with the new addition of cloud upload, which gives our vehicles the wisdom of the crowds by uploading real-time, worldwide roadside information from all of our vehicles around the world. Our imaging radar, a high-resolution imaging radar, which is stated to be second to none, not by us, by the way, by our customers, provide true sensor redundancy to our vehicles. And finally, we're able to formally measure this by an academic concept that was developed by our founders to actually measure the safety level of our vehicles. And just as a small teaser, this is what we do with our imaging radar. We provide a 4-dimensional high-resolution point cloud in real time to our software, providing it the ability to take it to the next level of autonomy in vehicles. But back to the technical. So, as our imaging radar is aimed for the drive assist autonomic vehicles industry, we must adhere to the road vehicles functional safety. And the standard comes with requirements, with huge requirements that impact our whole solution architecture and also our DFT requirements and targets. One of these requirements is to actually keep detecting faults in our devices even after it's been deployed. Okay, throughout the entire life cycle of our product. We accomplish this requirement by using the Tessent MissionMode solution, which actually enables us to keep testing our device, what we call in field, after it's been deployed in the vehicle. So this is how we test. We can keep testing our device throughout the entire life cycle of the product. So for those of you who are not familiar with the concept, I'll describe it in high level. So Tessent MissionMode is built out of two main building blocks. First one is the IST, the part on the left. Let's see if I can mark it here. This whole part here, the IST controller, in-system test controller from Tessent, along with an internal CPU and some memory. This logic enables us to actually take over the tap controller instead of the AT tester, okay? We can take over the tap. Tessent provides us with some software that we can program. We can download to the memory and program our CPU, and then initiate an AT test, a mission mode test, to the second building block, which is the BIST component. The BIST component can be either a logic BIST component, aiming for standard cells faults, or a memory BIST component, checking for memory BIST faults. In terms of the BIST component itself, eventually it's transparent whether we're in a tester environment, which is driving the test, or we're in field and we're driving the test from an internal CPU. But now if we think of it, what happens if the mission mode logic itself should have a fault? Okay, as said, we're required to keep testing our device periodically, and should that logic fail, we won't be adhering to the standard requirements. So I divide this up into two phases. Okay, if we're already in field and this logic should have a fault, the first mission mode test will actually fail, so easily detected. But how do we actually make sure we cover this in production phase before we deploy our device? Okay, and of course that's important, right? If that doesn't happen, we won't be compliant to the standard. So how is that done? So Tessent provide us with actually two approaches to test the mission mode logic. One is the one on the left. First one is called controller chain mode. It's actually a non-compressed scan chain implemented at the RTL level of the controller, which then enables us to run a standard scan test on the controller logic using scan clock, scan interface. And then we have another option to use a JTAG-based directed pattern. They're aiming at the BIST component directly. Okay, again, using test interface, using JTAG interface, TCK and test interface. So again, both these options come out of the box from Tessent, but as you can already see, both use a dedicated test interface. Now, how does it look in real life? In real life, if we look at our imaging radar design as an example, okay, our design is built out of multiple physical partitions, some duplicated, some unique, but all of them have the dedicated test logic for enabling the mission mode. And all of them are interconnected, and all of the design is interconnected by a network on chip with a NOC controller and of course can be accessed via tap. If we zoom into one of these partitions, we'll see the complexity of each partition with several clock domains and internal clocking sources. We see clock domain crossings, synchronization schemes. There are dedicated interfaces. All of this logic enabling the actual mission mode capability and the real design. So in real life, things are a bit more complicated. And as opposed to the conceptual design I showed earlier for explaining what mission mode is, in real life, there's a need for additional coverage. Now, I'll just say that when rehearsing this presentation, I was kind of thinking, okay, what am I actually saying? That Tessent is lacking in their solution, but the answer is no, because eventually, Tessent provide the mission mode capability, but when you think of it, mission mode takes the DFT world into the functional world. It's already crossing the boundaries from your standard DFT logic and test logic. If you think of scan, MBIST, you don't need to test your test logic during production. If your scan logic is broken, all your scan tests will fail. For MBIST is broken, the same. But when you talk about mission mode logic, there is more to it. It's already crossing the boundaries into your functional world, and eventually you're running the mission mode under your functional scenario with your real clocking schemes, synchronizations, your custom logic, and Tessent can't cover that for you. This is why it's important. If you intend to use mission mode logic, you need to remember that mission mode is already crossing the boundaries to your functional logic, to your functional scenario. And it's up to you to actually cover that during production. Otherwise, you might have faults in your design which are not covered during production. So in terms of problem statement, if we visualize this, we have the out-of-the-box Tessent test approaches covering our Tessent mission mode controllers, or IST controller and the BIST component that we mentioned earlier. But our own custom logic and custom interfaces are not covered by these solutions. So how do we overcome this? Okay, so in our design, as mentioned, all of our design is actually interconnected by this NOC controller. This NOC controller can actually provide access to mostly all of our registers in our design. As of such, if I can program my NOC controller, I can use it to program the CPU. Just as if it would download in the real life scenario, it would download code from the memory. It would be programmed from the memory. I can program it through the NOC. But how do I access the NOC on the tester environment? So we have our proprietary logic of a JTAG to NOC converter. Using this JTAG to NOC converter, we are able to drive JTAG patterns on the tester, which are converted by this proprietary logic to NOC transactions. And in turn, the NOC controller will drive or program the CPU with the Tessent generated software to initiate a mission mode test. And again, as I said earlier, from the BIST component perspective, it's transparent. From there on, once I initiate the test, I test the device with the actual real functional logic, with all the functional clocking, with all my real clocking and the synchronization schemes and the real custom interfaces. In this manner, I provide the missing production coverage for all our custom logic. So this is, in terms of problem resolution, we enhance the coverage and use our proprietary logic to exercise the real data path with all its complexity. So again, to summarize, and I'll pass the presentation to my colleague Pavel. To summarize, if you intend to use mission mode logic, you have to remember that your actual logic is involved, and it's up to you to make sure you cover it during production so that you safely deploy your products in field. So with that, Pavel will take you through the details of our solution.
All right. Works. Hey, hello. So my name is Pavel. I come with 7 years of DFT experience. Last year, I joined Mobileye company, and I've been mostly responsible for implementation of the LBIST and IST inside the imaging radar. So, as my colleague previously mentioned, like we proposed this new approach for production testing of our mission mode logic and the modules that are interacting with it. So in this picture is similar to the previous one, but maybe gives a little bit better description of how the data is sent through our design and back. So once again, basically, if we look at the picture, we can see that we have our standard path, the upper one, which connects our TAP IJTAG to the IST controller, which allows us to run our BIST test through the ATE and basically bypassing the IST controller. So this path is not exercised in our solution. Instead of that, we are instead of as previously mentioned, we are using this middle path, which exercises the network on the chip, which allows us to program the CPU from the ATE and receive the pass-fail status. So to run the whole pattern or to whole test, like just exercising the BIST component is not enough, right? So first we need to initialize our chip in functional mode, so it operates as close as possible to our in-field testing. So it means we need to reset the design, turn on the proper PLS, the power domains, all sorts of configurations. Once this is done, we can enable dedicated tab, which handles our JTAG to NOC module, which is responsible for translating the JTAG sequence to the NOC transaction. For the NOC transaction, we need the NOC address plus the data that we want to send. And the data is actually based on the payload which is generated by Tessent. So once the data reaches the CPU, then the CPU through the custom interface drives the IST controller. We put some special custom interface in front of the IST controller, just to make sure that the clock synchronization and the data latching between the CPU and the IST controller is done correctly, and we have high confidence in it. So once the data reaches the IST controller, from there we can use the standard IJTAG network to perform like an in-field test through ATE. Can be LBIST, can be memory based, can be any IJTAG-based test. And then at the end, of course, we get our signature from the BIST component, which is transported back via IST, via CPU back to AT, where we can compare against the expected one. So in case we detect the failure, it means the periodic testing is not available, the chip is broken, there is no point of any further testing of this particular chip. So now I would like to dive deeper about the data that we get from Tessent and how it looks like. So when we use Tessent IST controller, especially in this particular case, we use IST controller with like generic CPU interface. And this is the example payload that is generated by Tessent. Basically, as you can see, it consists of two types of data. The first one is the data or information to the CPU. So how the CPU should perform next action and how to act on the data. And those are indicated with the ins or start with the ins. And as an example, in the first line, we can see the instruction wait, which is that the opcode is 110. And in the next line, it tells the CPU how many clock cycles it should wait before performing any other actions. Another example of CPU instruction is data x compare. It means that the next, in this example 3, IJTAG instructions will consist of x value, and so the response from the IST controller first needs to be masked and then compared. And then in the bottom one, we can see two example IJTAG instructions. So this is actually the data that needs to be delivered to the IST controller. Marked in the blue, we can see the opcode 01, and then the write data that needs to arrive at the IST controller. In the second line here, we can see the masking value. So basically, we want to mask out the two most significant bits and compare all the rest. And the third line is the actual expected data that will be coming from the IST controller, and we can compare. So this is what you get from Tessent. It's really helpful, but in the end, it's not a format that could be easily translated into ATE format. Plus, as I mentioned previously, we need some more information like the chip initialization sequence plus the NOC addresses. So here comes the SVF, serial vector format. So this is our chosen vector to deliver the pattern to the ATE team. So as you can see in the picture below, it's example SVF format with some tasks, and like just as an example, we can see that the green circle here, which corresponds to the Tessent generated payload translated into SVF task. And as previously mentioned, along with the data, we also need to provide the NOC address. And the choice of the SVF format was mostly, there are two reasons, right? The first reason is because it's quite easy to read, and actually the AT engineers are able to update the SVF on the fly, especially when it comes to the initialization sequence or the NOC addresses. The other reason is that the SVF is supported by Tessent. So in case we need to change the format in the future or do anything with it, Tessent can translate the SVF into PDL, and from that to wiggle or style. And in the end, like as a summary, using Tessent MissionMode enables us to meet the standard requirements when it comes to periodic testing, but because of the design choice on our side, it does not provide and it cannot provide the coverage of our CPU and the IST interface, which is custom logic. So for that, we decided to utilize the JTAG2NOC proprietary instance to be able to run like functional test of mission mode logic from the ATE. So we can easily screen the defective parts or be more confident in our mission mode logic at the production test. And as a bonus, like this kind of check the checker approach is kind of popular in the AV industry and give us much higher reliability. And as a bonus, I guess, like the first, of course, the whole solution was verified in simulation, but as of recent, we received our silicon, and we can say that it also works on the real silicon. And that's it.